Hello everyone, this is a video lecture for Calculus 3, section 12.5, Parametric. Okay, so what does parametric mean? Well, parametric equations we've seen before back in pre-calculus. This is more so parametric lines, but really we're going to see how it goes. So, parametric in general, what does it mean? That you have t's all over the place. And so you're going to be using t's as your independent variable, essentially. Very often, they'll be asking to find r of t, and that is a vector that you'll have an x, y, and z in here. But the x, y, and z obviously are going to be t's. So another way that they'll sometimes want it, they'll say x of t, y of t, z of t, equals, and then they'll have a big old box here. And so you're basically, it's the same thing. It's the same answer here. You're just putting it in a different format. Here's some formulas for you. That r vector basically is your initial point plus the terminal point minus the initial point. I'm trying to make it look good there. And then times t. Let me put a time sign just to emphasize that. Times t. That's one formula. Another formula could be, if you have a point and a vector in particular, your point plus your vector times t. So that's another way to do it. Okay, well, let's get started. So I got 12.5.003. And so they give me a point, 6, -5, and 4. And then they give me this vector, 1, 3, -2/3. And they're wanting to know what r of t is. And so it's a vector, of course. I start with 6, and then I'm going to go one distance for every t. I start with -5. I go 3 distance for every t. I start at 4, and then I go a -2/3 distance for every t. And that is your answer. You're done. Very simple. They're again wanting that x, y, z. I guess kind of like in a point form, kind of. But really, it is literally the same answer. So let me just show you. 6 plus t, comma, -5 plus 3t, comma, and then 4 minus 2/3 t. Same thing, nothing changes. Next question. So, as I keep going, a lot of the times I'm not going to remember the words they were using. I just know how to do it. So, there's probably some words in there that I'm skipping. This is a point, and we're going in the parallel direction of this vector, or we're going with the perpendicular of that plane, and all that kind of stuff. There's a lot of verbiage that I might not be able to remember when I'm going through all this. Anyway, so this time I got a point and a line, and this line is parametric already. So that's kind of funny. So they're saying they want to redo this, but starting from this point. They want a parallel line, but then starting at this point here instead. Parallel, if you really go down to it, you got two parallel lines like that. What do they share in common? Is it their y-intercept? No. What is the same for both of these lines? Is the slopes. The slopes are the same. And so we're looking at our slopes. And if you remember, slopes are kind of like mx plus b. It's that m part. It's the multiplied scalar next to the independent variable. So here is 3, -2, and 8. That's your slopes, I guess you can kind of say. So we're going to basically use those 3 numbers as my slopes, finger quote, slopes. And so for my r, I'm going to start at 0, and then I'm going to go a slope of 3t. I start at 13, and then I'm going to go a -2t, and then -6, going a +8t slope. there you go. I don't remember if they're also wanting you to make a point form out of this one or not. Obviously, it'll be all the same. I'll also notice that I'm using just R instead of R a T all the time. That's just my notation. Okay, next one. I have a point 0, 1/2, 1. And then I have another point Q, which is 6, 1, negative 2. And they're wanting to know what R of T would be. Again, I got 2 points now. I'm going to go way back up to this other formula we had earlier. Oh, sorry. This one. So terminal and initial points and all that. And so then looking at my x's, I have my terminal point. I'm sorry. I start with my initial, and then I have my terminal minus initial, and then times t. And the same for each component. So I start with my initial, and then plus, and then I have my terminal minus the initial, times t. Last one, starting with the 1, and then I got the negative 2 minus the 1 now, and then times a t. So here's something about it. My answer is correct, but it was not the same as what my math lab had on this one. I'm not saying that they're wrong, or even if I'm wrong, they're really the same thing. It's just that they have it formatted a little differently. Like, it literally is different. It's different. And yet I know that mine should work. If for some reason it doesn't work, maybe I didn't read the directions well enough, but I saw this one here as my initial point, and this is my terminal point. Now what they did is they flipped them. I don't think I saw something that would make that wrong. Anyways, with this one they're asking for these symmetric equations. Symmetric equations. And this is kind of weird because what you're doing is that you have an x, a y, and a z. X is this is y, this is z, and what they're wanting to say is t is equal to, and then some kind of equation with an x in it. So like here, let's start with this one for a second. I essentially have x is equal to 6t, but I want t equals. So what do? Divide by 6. And so then t is equal to x over 6, and that is your first symmetric equation. Notice they're all equal to one another. Kind of weird there. The next one here, I got 1/2 plus basically half t, and this is again y equal to that. So how do I get t equals? I move this over, and then I divide, and so then I get, yep, there we go. Yeah, we're good. My t equals y minus 1/2 divided by 1/2. Now, could you simplify that? Oh yeah, definitely. I'm just saying this is how you would put it if you had to. And over here, that's a negative 3. So I have right now z is equal to 1 minus 3t. If you go back. To get t by itself, I minus the 1, divide by negative 3. And so then I got z minus 1 over negative 3. And this is basically your answer. What the symmetric equations don't ever tell you, sadly, is that it's t equals and then all this stuff. Very simple to actually do this, but when they approach it, it's very confusing because they don't ever say t equals for some reason. I don't know why. So just watch out for that right there. One other thing is that this right here is technically wrong because, again, I had gotten this one wrong, finger quotes. But it's not. So this right here, because it's multiple choice, when you go and click it, you're not going to have the exact same thing. I would say look for something that's similar to this. It's going to probably have like a -6 or something like that here. Again, I'm not entirely sure. I'm not really worried about it. So there you go. They were using their answer, which they think is correct, to go and get this. Again, mine is equivalent, I know it, but then again, my symmetric equations will not match up to theirs. Okay, next question. So 12,5,010, I have a point 310, and then they say perpendicular to these other two vectors. So perpendicular to two vectors, and they give me the vectors 110 and then 011. Do you notice something I already did? I made it a cross product. Because in order to get something perpendicular to other vectors, you're going to take the cross product. So let me rewrite this the way I like it. So 0 always in the front. 1 times 1 is 1, k component. 1 times 1 is 1, negative j component. 1 times 0 is 0, always 0 in the middle. 1 times 1 is 1, that's a positive I component. Anything times 0 is 0. So that makes it easy. 1, negative 1, 1. There we go. Actually, you know what? I'm not going to box it. I'm going to circle it because it's not a real answer yet. I just found the perpendicular slopes, I guess you can say, for those two vectors. And so I'm going to combine it with my point now. So here we go. Here's my R now. Oops. Do that a little bit better. My point was 3. My slope is a 1, t. My point was a 1. My slope was a negative 1, t. My point was a 0. My slope was a 1t. And there's your R. There you go. They want the symmetric equations here. Let me go ahead and say t is equal to. So again, this is x, this is y, this is z. So x equals all this. I subtract the 3, and we should get it. Again, equal signs for all these guys. So here we're basically here. Let me rewrite this. I'm saying that this is 3 plus t. I'm saying here that y is equal to 1 minus t. And then here I'm saying that z equals t, essentially. So here to get t by itself, minus the 1, change the signs. So it's actually going to be 1 minus y in the end there. And then z equals t is literally the same thing, so you just put that there. There's your answer for the symmetric equations. Okay. Next one. 12.5.01, 0.12. So they give me a point, 6, negative 1, negative 4. And they say, find the plane parallel to this other plane. So find the plane that's parallel to, well, here we go, 2x minus y minus z equals 7. Put a little dash mark there maybe. Okay. It just looks cooler. This should be the parallel symbol. That was really bad looking. They're wanting a plane. So they want a plane equation for all this. And so what it's going to look like is ax plus by plus cz equals d. And it's supposed to be parallel to this one. The thing is with these planes, it's kind of like a sheet of paper in space. They all have this thing called the normal vector. I use capital N. You can use a little lowercase n. It's all the same. The normal vector, which is right here. 2, negative 1, negative 1. That's your normal vector for that. It's coming up at 90 degrees. That's my little thing here. And I'm saying it's 90 degrees from the paper, straight up out of it. Right-hand rule and all that stuff. Well, this is a way to say what the slope is of that plane, okay? So that's my slope. And if it's parallel, then my slope doesn't change. Therefore, my answer, I know for sure, is 2x minus y minus z is equal to d. See, I don't know what d is right now. I have to go and find it. But they say I'm going to be using this point, and then it's going to be parallel. So here's my second plane here right quick. There you go. And there's my point P, I guess I'm sitting on. So it's going to be the same kind of idea, but I just shifted it up or down, and that's what this is they shift up or down, essentially. And so how do you find it? Well, you know that this is x, y, and z, so you plug them all in, and, well, you're done. So, oops, that's going to be minus a negative 4 equals d. 12 plus 1 plus 4, and so then we got, what, 17 is equal to d. And so my final answer, kind of mushing these together, 2x minus y minus z is equal to 17. There we go. Let me pause the video for just a second. All right, and I'm back. So let's do another one. 12.5.031. So they say to find a plane going through these points. So they want the plane as the answer. And they give me these points here. 0, 6, 6, 6, 0, 6, and 6, 6, 0. They couldn't just do something plain and basic like 1, 2, 3, 4, 5, 6, 7, 8, 9. That's okay. So how does this work? Well, they want the plane, and what we need to do is find that normal vector here, which is basically kind of like the slopes. And how do you do it? Well, what we have right now are 3 points on this plane right here. So you can kind of think of it like there's a triangle, and the plane extends out from that triangle. And so I'm looking to see about how to get this vector right here. Well, it's orthogonal to all this. That's that 90 degrees right there. How does that work? Well, I can make 2 vectors from one point, and then I can do the cross product with these 2 vectors to find that third orthogonal vector. So what I'm saying is that I'm going to take this and combine it with this one, and then I'm going to take this and combine it with this one to make 2 separate vectors, kind of like an A and a B. So 0. Well, remember, this is actually from pre-calculus, terminal minus initial. And so I'm going to say 6 minus 0, 0 minus 6, and then 6 minus 6. Well, it's 0 actually. Well, I'll write it out, I guess. My B vector, same thing, terminal, and then minus initial. 6 minus 0, 6 minus 6, and 0 minus 6. So 6, negative 6, 0, 6, 0, negative 6. So these are my 2 vectors, which I now will cross. I'll just go ahead and put it down right here, I guess. So always a 0. 6 times 0 is 0. And 6 times 6 is a 36. That's a negative 36. But that was also a negative j component. Keep cruising. Negative 36, but that's a negative k component. Always a 0. And 6 times 6 is 36 right here. That's a positive 36, along with a positive I component. The last one here, 0 times anything is 0. That makes it easy. I component, 36. J component, 36. K component, 36. And what you could do, this is really cool, this is your slopes, I guess you can say, or your normal vector. Again, I use little n, cap n, whatever you want to use. And so what do we got here is the slopes. What you could do, technically, is make it into like a unit vector. Now, I'm not really wanting to go for unit, because that would actually, it would look weird. You would have like the square root of 3 all over the place. So it's not really unit, but I'm saying you can like reduce it with a scalar. If you want to, you can do a 1, 1, 1 right now. I'm not going to do that, but I will have this effect at the very end. So I'm just going to roll with it as if I never saw that. 36, 36, 36. That's what I'm going to be using. And so that's my slopes, right? So then my plane equation will look just like this. And then, of course, D, which I don't know. Well, you can plug in any point you want because, again, all 3 of these are on that plane. I'm going to pick the first one just because it makes sense, I guess. So that was, again, 0, 6, 6. Okay. So then we got 36 times 0, 36 times 6, and 36 times 6 is equal to D. And I got a really big number, which was 432. So then my final answer, here we go, 36x, 36y, 36z is equal to 432. Woohoo! This should work. If you want to reduce it by saying divide by 36 on both sides, then you would get that single 1 everywhere. So 1x, 1y, 1z, and then it equals simply 12. That's a lot cleaner. So there you go. next problem. So this is 12.5.045. They give me a line equation, xyz, and then, so that's actually one big line right here, okay? They also give me a plane equation. That's a plane. So I have a line and a plane, and they say, where do they intersect? Where do they intersect? In a weird graphical sense, I got a plane out there, and then I have some kind of a line, just kind of, there you go. And it probably collides somewhere around right there, let's say. So they're wondering, what is that point P where they would collide? Now, if you're thinking for just a second, like, what if this line was over here? It would never touch that plane. That plane technically extends out forever. I mean, it's an infinitely large plane. I'm just making it look a little more large there for you. It goes out forever, so you would eventually be touching somewhere. Okay. So how does this work? Well, look at this. I got x equals something, y equals something, z equals something, and I got an x, y, z. What if I just took x, y, and z and plugged them in? That's what I did. So 2 minus 2t plus 2 times 3t minus 1 plus t equals 7. See how I'm plugging them in to each of those. And then solve for t. And so when you do all this math here, blah, 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 I think I get t equals 2. I'm just going to skip ahead because why not? T equals 2. Great. But that's not my final answer. I figured out t equals 2, but then what is my x, y, z point? That's really what they're trying to find here. What is x, y, z? Well, I have a line with t's and stuff, so, oh yeah, t equals 2. I can plug it in there, there, and there. So then x equals the 2 minus 2 times 2, which is negative 2. Y equals the 3 times the 2, which is now 6. Z is equal to the 1 plus the 2, which is 3. And so there you go. Final answer. X, Y, Z equals, big box, negative 2, 6, 3. Okay. Ta-da. Okay. Next one. Keep cruising. 12.5.054. So I got an x minus y minus 7z is equal to 1. I got 7x plus y minus z equals 2. And they're wanting to find the angle between the planes. Angle, well, you heard me, between these two planes. So what we have is we have two planes here, and let me draw another one. I don't know, something maybe like this. And so it's kind of hard to imagine on 2D here, but in 3D, you got two pieces of paper that are touching and colliding. So I'm just going to make this one up here, just maybe something like right there. Okay. Cool. So that's the goal. They're intersecting. What's the angle between them? So let me reduce this down into 2D land if that's okay. Because 2D land makes a lot more sense. Like, basically, I'd be doing this, and you're like, what? So let's not go there. Let's say I have 2D. In 2D land, you would essentially erase these guys, and what do you have now? Not planes, but lines. And so I have a line here, and then I got a line here, and I say, what's that angle between them? And that's really what's going to be going on. So it kind of looks like this if you kind of zoomed out, if your camera was like right here, and this is your camera looking down. You're probably looking at something like that. So what is that angle there? Well, obviously I'm not just going to get rid of my z's and stuff, because it's all in 3D land. So what I'm going to do is go back to a formula that we've seen before. Cosine theta is equal to a dot b over magnitude of a, and then magnitude of b. I'm just in 3D zone instead of 2D, and doesn't change anything. So here we go. I got 1, -1, -7. I got 7, 1, -1. And then I got the magnitudes down here. 1 squared, 1 squared, 7 squared, 7 squared, 1 squared, 1 squared. When you start doing the math here, 1 times 7 is 7. I got -1 times 1 is a -1. And then -7 times a -1 is a positive. 2 negatives make us positive there, 7. And then if you got 7 squared, it's 49 plus 2 more is 51. And those are the same. And so essentially we got 13 over, and when you mush these together, you actually just get a 51. This is the cosine of theta. And so then theta is the arc cosine of 13 over 51. Make sure you're in degree mode. So when you put it in, I got 75.23 degrees. Okay. Cool. Next one. Kind of move my colors there. I don't think you can see that. 12, 5, 0, 65. So they want the parametric equations, and I'm gonna go with this. Okay, I have a point 022, and they want to be parallel to this plane x plus y plus z equals 1, and perpendicular, yeah, I said it, it's okay, to x equals 1 plus t, y equals 2 minus t, and then z is equal to 2t. Okay, what is going on? I'm parallel to a plane, and then I'm perpendicular to another line. It's a line right there. So as a plane, the plane itself has this normal vector, which is perpendicular to itself. So that's kind of weird, but this slope here, 1, 1, 1, is this vector right here. Okay. I have another line going on, so I don't know. There you go. There's a line. Actually, it's one directional because it's t positive. And I'm supposed to be perpendicular to this guy as well. And so it's kind of weird. It's like I'm perpendicular to this, and then I'm parallel to the plane. So I'm actually like somewhere down here. But yet I'm perpendicular to this guy because, again, by definition, that's a normal vector. So it's a line that's on the plane, but then I have these other two things going on. Very strange. And that's why I don't think the visuals are going to help that much. Instead, we can just see these as two different vectors. So then I've got my 1, 1, 1, and then I've got my slopes. My slopes in there, if you can notice, 1, -1, 2. And in order to get perpendicular to this and parallel to that, I guess it would already be perpendicular there, you cross product. So there you go. There's your, I guess in a way, your formula. Always a 0. 1 times -1 is -1 in the k slot. And we got a 2 in the negative j slot. Well, that's good enough. 1 in the negative k slot. Always a 0. A 2 in the positive I slot. 1 in the positive j slot. -1 in the negative I slot. And then a 0. Putting all my ij's and k's together, so these guys here, two negatives make a positive. 1 plus 2 is a 3. My j's here, you can see I got -2 plus 1 is a -1. And then finally, these two guys right here make a -2. So this right here is, again, my slope of that line they're wanting. And then finally, we got a point that they made, that they gave me. So I'm going to use that point 022. And here we go. So I got my slope, I got my point. Here we go. My r vector is 0 plus 3t, 2 minus 1t, and then 2 minus 2t. And that should do it. Cool. I think I got one more question here. And here's the thing with this one. It's different than the others. And I looked at it and I was going to do it the long way, because I like doing things the long way sometimes. But then I got it wrong. So I went to the formula and I'm like, oh, okay. It's a distance from a point to a plane. Point to a plane. So conceptually, I have a plane, and again, there's this normal vector coming straight up out of it, and it's going to be hitting this point P. Now, this vector here is originating from a Q, which I have to make on the plane. And my goal, essentially, is that I have a point, and I have a plane. I don't know what Q is, but as soon as I know that Q, X, Y, Z, then I could just simply say, well, that distance of that vector there between 2 points, Pythagorean theorem, and you're done. So my point that they gave me is 1, -4, 2. My plane is 3x plus 2y plus 6z equals 5. Okay. Now this is an x, y, and a z here. This is an A, a B, and a C, and a D, if they're asking for it. There's actually a formula for this. Capital D, which is your distance. I'm just going to go ahead and give it to you. AX1, which means that guy right there. And then BY1 plus CZ1 plus D, and then that's the absolute value of that thing, all divided by the square root of A squared plus B squared plus C squared, and that's it. I'm not going to do it. Honestly, I tried to do it the long way. It didn't work, so I'm just letting y'all do the formula, and that's it, actually. All right. Thank you very much. Have a great day.